Hey folks, so we're going to keep looking at network circuits, but we're going to build off of the conceptual video, and now we're going to move into the mathematics that we see that exist within our network circuits as well. So looking at the same two circuits that began the previous video lesson, right, we're going to see that we need an order of operations, right? The idea that we want to solve internal first, then look at the overall. So we want to look at what is on the inside part of the circuit, then move to the outside part of the circuit. And we're still going to obey by our rules that we saw from the individuals. So what that means is on the left-hand side here, right where we have our parallel path that is within the series circuit, what we would want to do is we would want to solve the parallel first. Then we would want to go through and then we would solve the series, right? So notice that we're looking at the internal resistances first, in this case are in parallel, then we're going to do the overall, which would be the series. That is why this is a parallel circuit that is in series. If we look at our one to the right here, the series path that is in parallel, we would want to solve the series circuit first, then we would solve the parallel circuit. So again, what this shows us is we're going to look at the inside circuit first, then we're going to look at the outside, right? Solve these things inside, out is how we want to go about this. What that's going to let us do, because the whole idea of simplifying these circuits is to get two devices, how would they behave if they were one? Same thing here. We have two devices. How would they behave if they became one? Because when we find a total resistance, that's what we're ultimately trying to do is how would this entire circuit function if it were a single device rather than two or three or four or however many that we have. So main idea here, inside, out is how we want to go about this. And when we look at our individuals, here, we would abide by our parallel rules, so we'd look at all the reciprocal functions. Then we would look in series and abide by series rules. Here, we would do our series rules first, then we would abide by our parallel rules. So, first thing we got to do, right, figure out what is our network type. And here, we're looking at a parallel in series. Again, because resistors 2 and 3 are parallel, and 1 is in series with each of them. Trace the path. If you go through 1, you have to go through, right? So when you go through 1, you then get to 2. You go through 1, you get to 3. That's how we know that 1 is in series with both 2 and 3. 2 and 3 are parallel to one another, right? So there we have our type. So our inside resistances here are going to be our parallel ones, which means we're going to use our reciprocal rules to be able to find what our total resistance is. Then we look at the overall, or the outside, right? The whole inside-out method of solving this. So our overall resistance, because now we're in series, this R of T, this is really representing our parallel total. That's going to come down here, and now we're in series. So the total in parallel plus R1, which is in series, is what's going to give us our total. So really, this is representing our parallel total is what we get here, right? So our parallel total is in series with R1. That is where this is going to come from, right? That's what we're going to see here. If we look at the other type, same deal, right? Order of operations. What type of network circuit do we have? This would be our series in parallel because our internal circuit is going to be in series. The overall is then going to be in parallel. So first, we would use our series rules, which is going to be adding these together. So our total in series is R1 plus R2. Then we look at the overall, or the outside, because 1 and 2 are in series with each other, but they are both parallel to 3. Trace your path. If we take the first branch, you have to go through 1 and 2. That's how we know they're in series. If you take your second path, you're only going through 3. That's how we can determine that 1 is parallel to 3, 2 is also parallel to 3, but 1 and 2 are in series with one another. So then our overall, we're using the parallel formula here, where this R of t now is representing our series total. And that series total is going to go in the denominator here because now we're in parallel. Because the total of 1 and 2 in series is parallel to resistor 3. So we have our two devices that are now in parallel, 1 over the total resistance of this circuit then. So we're going to have to work that reciprocal to find what that true total is. Now a little bit of practice here, right? So as we look at this one, here's a slightly different type of circuit. And if we look at this one, depending on which way you go, whether you go from positive to negative or negative to positive, we're going to see the same trend. If we go from negative to positive, we have to go through R3, and then you choose either R2 or R1. So R1 and 2 we can determine are in parallel. They are both in series with 3. If we go positive to negative, we choose, right? So we choose the branch of R2, then you must go through R3, or you choose the R1 branch, you must go through R3 again. So what we can determine is we have a parallel circuit between R1 and 2 that is in series with R3. Notice again we're using kiloohms, which is going to be times 1,000. So really, we're looking at 3,000 ohms, we're looking at 10,000, and we're looking at 5,000. Right? Always got to keep track if there's that kilo ohm in there or not. So if we want to find the total resistance, again, looking at this being a parallel in series, here's how we would go about this. Our parallel circuit is our inside circuit, so we would want to solve that first. Right? We have our parallel circuit, which is nestled in series with that third resistor. So our parallel circuit is going to be R1 plus R2. So we've got 1 over 3,000 plus 1 over 10,000, because that's how we would do this in parallel here. We get a really small number, take the reciprocal, and we get about 2,300 ohms. Because this is in series with the 5,000, now we can add these two together, and we're going to get 7,308 ohms is going to be our actual value. If we're looking at sig figs on this, because each of these is just one sig fig, we would call it 7,000 ohms. If we went 2 sig figs, or let's say it was 3.0, 10 with a decimal, and 5.0, we could call this 7,300, right? Depending on the amount of sig figs, we're going to see that this number could be 1, 2, 3, 4, or more sig figs. That's how we would look at finding the total resistance. Again, doing the parallel first, then adding it because we're in series. Knowing what our total resistance is, then we have two questions that we can ask. Well, what's the current through each device? Or what's the voltage? Because we know we have a 9-volt system, it's actually going to be easier to start by finding the voltage in each location, right? That's actually going to be something that we can do relatively easily because we know the total voltage, we know the total resistance, so we could find the total current first and then work backwards. So what we would want to do is look at all of our totals and set it to find the total amount of current. Doing this, we can isolate Ohm's law, rearrange it to solve for I, get our total voltage, our total resistance, to get the total amount of current in the circuit. Now you should already be thinking, hey, the total amount of current is what's present in any device that's in series, so you can already think ahead and know that the total current moving through R3, the 5,000 ohm device, is going to be this 0.00123 amps. We can look at the voltage across each device then, and we're going to start with the one in series because that is going to be different from the two that are in parallel. Because we know the total current and we know the 5,000 ohms of resistance, we can figure out with Ohm's law that it draws 6.16 volts. Again, the importance of recognizing that the total current is going to be present in the series part of our circuit. So we take the total current because it's all moving through this device times the resistance to get 6.16 volts, which tells us that the voltage that is left over is 2.84 volts. and because R1 and R2 are in parallel with one another, they're each going to get the same voltage because the voltage down each branch is going to be the same. Because 6.16 volts has already been used, the remainder will go to devices 1 and 2. That way, each loop is going to have a full 9 volts. Here, if we have 6.16 volts for R3, each branch getting 2.84 shows us that loop. Here we have a 9 volt loop, and here we have a 9 volt loop. Now if we look at the current through each resistor, because we know the voltages, right? We know the voltages across each device. Now we can utilize Ohm's law to figure out the current, right? Because we know voltages, we know resistances, so we can find current using V equals I times R. Again, drawn from the previous slide, we already know the total amount of current, and we can verify that with our calculation for the current moving through device 3, where we have 6.16 volts, 5,000 ohms. We see that that current matches the total as it should, because all of the current at some point must pass through that device. Then we go to devices 2 and 1 here. So if we go to device 2, 2.84 volts at 10,000 ohms is going to get us a very small amount of current, 2.84 times 10 to the negative 4th amps. Same process, but using 3,000 ohms now for device 1, and we are going to get more current, 9.47 times 10 to the negative 4th. Think about this here. We have more resistance, so we have less current. We have less resistance, so we have more current. But we add these two together, and we're going to get back to the total. So that is how we're going to do our math behind our network circuits. It's about working inside out, identifying the internal circuit, and then figuring out how to solve that one through, then solving the outside or the external or the overall circuit, right? Lots of different ways to go about it. So using Ohm's law is really what we see here. This verification of Ohm's law at different locations in the circuit to be able to show that all of our voltage is getting used and that our current is going to be represented everywhere in the circuit, whether it gets split down a parallel branch or whether it's all flowing through a series part of the circuit. Thanks, guys.